So we're going to keep moving on. We're in section 5.2, and we're going to be working with something called medians and altitudes. Okay, both of those words you've probably heard before, so this should be not too difficult. So we'll start with defining what a median is. It's a segment from one vertex to the opposite midpoint. So it's a segment from one vertex to the opposite midpoint. All right, so that's easy enough. We're going to draw a quick little picture. All right, so we're going to have A, B, C, and we're going to draw a segment from one vertex to the opposite midpoint. So we're going to go from A, we're going to go over to BC to its midpoint, which looks like it's about right there. So that segment is called a median. So this is D. So we're going to say that AD is the median of triangle ABC. But there's a lot of other things that just happened by drawing that one little segment and calling it a median. Another fact now is that D is the midpoint of segment BC because of the definition of median. So when you're doing a proof, the definition of median might be something you'll use. Another fact here is that segment BD is congruent to segment DC. That's because of the definition of midpoint. Okay, so you might use this in a proof if you know something's a median. Well, then you can say D is the midpoint because of the definition of median, and then you can say the two pieces are congruent because of the definition of midpoint. One more little fact here. The point of concurrency of the medians of a triangle is called the centroid. Okay, so centroid is another vocabulary word we want to know. Centroid is where all the medians intersect, and we're going to have a centroid theorem, and it says that the medians of a triangle intersect at a point that is 2/3 the distance from the vertex to the midpoint of the opposite side. That sounds super random, doesn't it? So, as always, quick picture. Triangle A, B, C. And now we're going to draw all the medians in it. And I'm going to try to do them in different colors, so hopefully it helps out. So we're going to go from vertex to midpoint, where we think it is. Try to get as close as we can. All right, so those two are congruent. Then we're going to go from vertex to midpoint as best we can. And these two are congruent. And then we're going to go from this vertex to this midpoint. You can see I don't have my triangle drawn exactly right because these don't look right over here, but that's okay. It's thought that counts. And they all intersect in this one point right in the center, point P. Okay, so we would say that P is the incenter. And something else that's very interesting about this, we're going to label these points X, Y, Z. Something else that's interesting is this whole 2/3 business. Doesn't seem like much, but if we start to write it down, we're going to see that AP is equal to 2/3 of AY. Okay, that was our red line. So AP from A to P is 2/3. Well, that means that this part that's left over here is 1/3, right? So we could say that PY equals 1/3 of AY. If that makes sense. The big piece is 2/3 and small piece is 1/3. So if we go around and do the rest of them, we're going to say that BP is 2/3 of BZ. And PZ is 1/3 of BZ. And we're just saying that those little pieces are 2/3 of the whole or 1/3 of the whole. And the last one we have is CP, and that is 2/3 of CX, and also PX is 1/3 of CZ. Okay, it might seem like a bunch of gibberish right now, but the problems are really easy. I'll show you in class how to do a few of them. All right, next word is altitude. Altitude. And it's okay if you think about that as height, but just don't get the idea that it always has to be vertical. Okay, so an altitude is a segment from a vertex to the line containing the opposite side and perpendicular to the line containing that side. So quick picture. So A, B, C. And we said that the altitude is a segment from a vertex to the line containing the opposite side and perpendicular to the line containing that side. It's a fancy way of saying it's the height. Okay, so in our picture here, segment BD is an altitude of triangle ABC. And that's fine, that's all well and good, it's a simple picture, but we're going to complicate our picture a little bit. Just a little. So let's suppose that we have an obtuse triangle like this. Okay, so that one's not very good, but hopefully you draw a better one than I do. So this will be triangle ABC. And our definition said that it was a segment from a vertex, so from a vertex, to the opposite side, but it wasn't to the opposite side, it was to the line containing the opposite side and perpendicular. So for me to draw something from this vertex that's perpendicular to this, I'm going to have to extend this bottom out and draw it like this. And that's what it meant in the definition when it said the line containing that side, because down on the bottom here, from A to C is a segment, but there's also a line that goes through that you don't ever see. So in this picture, BD is an altitude of triangle ABC. And hopefully that makes sense to you, that that's the altitude or the height. All right, that's how tall that triangle is. All right, so we got all these altitudes now. So we're going to talk about what happens when they intersect. The intersection of all three altitudes of a triangle is called the orthocenter. So orthocenter, okay? It is where all the perpendicular altitudes intersect. When you get into something called vectors one day in your math life, you'll learn about something called orthogonal, and you know, it all kind of ties together, and hopefully you'll see this ortho stuff again. We're going to draw a few pictures. We are going to draw a simple, close to equilateral, but doesn't have to be perfect triangle. And we are going to draw a obtuse, definitely not close to equilateral triangle. So just like the one we drew up higher. Alright, so let's start with our simple one, triangle ABC. And we need to draw in our altitude. So from vertex to the opposite side and perpendicular, vertex to the opposite side and perpendicular, and from this vertex to the opposite side and perpendicular. Now, the good thing about this one is there's nothing fancy going on where anything's 1/3 or 2/3 or any of that stuff. So this point right here, P, is the orthocenter of triangle ABC. Alright, so that was the easy one. We're going to move to this one's a little more complicated. So we want to go from the vertex perpendicular. So let's just start with this one. We're going to go from this vertex, and we need to go through this side, but we've got to go perpendicular. So the way we're going to do it is to extend this line out. So now perpendicular looks like it's probably about right there. Fair enough, right? So now I'm going to go up to this one, and I need to go through this side, right? But I need it to be perpendicular. So I'm going to have to extend this one out and draw this guy straight down. Like that. And then I'm going to do my last one. So to go from this vertex and perpendicular to this side, well, that one's easy, right? You just draw straight over here and perpendicular. But they don't intersect, right? I just got these three random lines. It doesn't look like this picture up here. This was like some kind of broken puzzle or something. It doesn't work. So what we have to do is extend these lines. And what happens is our orthocenter winds up way outside of the triangle. So P is still the orthocenter of triangle A, B, C. And we're going to draw a quick little table here to help you. So when you have an acute triangle, the orthocenter is in a certain place. when you have a right triangle, it's in a certain place, and when you have an obtuse triangle, it's in a certain place. So we're going to draw an acute triangle. We're going to draw a right triangle, and we're going to draw an obtuse triangle. All right, acute's easiest, okay? The acute is always inside the triangle. It's pretty easy. Bunch of little right angles, bunch of heights, everything's good. On a right triangle, not so bad. So we go from here to the opposite side, here to the opposite side, and since it was a right triangle, right, they all intersect right here. So that's our orthocenter. Now the obtuse triangle is where we get a mess going. So here to the opposite side, perpendicular. Here, opposite side, perpendicular. And here, opposite side, perpendicular. So these are absolute messes to look at. But don't worry, it's not going to be a test with 35 of these on it. It's going to be a quick question and you'll be done. That's it, and have a great day.